Algorithms for edge AI have to make good decisions under tight limits: low power, small memory, and fast response times. The focus here is how model design and inference choices change when the computation has to run close to the device. Continuous sensor data has to be made usable before any model can act on it. The central problem is turning a live stream into input that edge AI can process reliably. An edge device usually sees readings arriving over time, not isolated examples handed to it on demand. That means the first job is to convert raw flow into something a model can classify, detect, or predict without losing the meaning in the signal. Windowing is the basic way to make a stream model-friendly. By cutting the flow into chunks, the system can examine one piece at a time instead of trying to reason over an endless signal all at once. A few seconds of temperature, vibration, audio, or chemical data can be bundled into one window and passed downstream as a single unit. The model is not holding the whole stream in memory as one thought. It keeps revisiting short slices of the flow. Latency tells you how long one chunk takes to process, and frame rate tells you how often a new chunk gets examined. If either one is too weak, the device falls behind or checks the stream too infrequently, and brief events start slipping through. That matters most when the event is brief. A spoken command, a quick motion burst, or a sudden anomaly may happen between checks. And if a system never samples at the right moment, the event is gone before the model ever sees it. Overlapping windows are one way to recover short events that do not fit neatly inside a single chunk. The benefit is better coverage. The cost is that the device has to process some of the same data more than once. If an event starts near the end of one window and continues into the next, overlap keeps it from being cut off by an arbitrary boundary. That extra shared region gives the model another chance to see the full pattern. The price is extra workload. On a constrained device, repeated processing means more compute and often more power use. So overlap has to be chosen deliberately rather than treated as free insurance. Window size changes the whole behavior of the pipeline. Larger windows give more context, while smaller windows respond faster. So the right choice depends on what kind of event you need to preserve. A larger window can help separate noise from real structure because the model sees more of the signal at once. A smaller window makes decisions faster, but it may not contain enough evidence for a stable result. Slow environmental drift can tolerate longer windows, but a quick burst of motion or a short command usually needs shorter windows, higher frame rate, or both. There is no universal best setting. The right choice is the one that matches the event. Algorithm choice also changes the amount of context you need. A threshold on a derived feature may work with a small slice of data, while a sequence model may need a carefully shaped window because meaning appears across time. The same stream logic applies when the data is video. A camera feed is continuous too, so the model still needs frames or short frame groups that preserve motion without losing temporal context. If analysis is too slow, a brief action can happen between samples and never enter the model. If the window is too short, the image sequence may not hold enough context to tell real motion from background movement. Digital signal processing sits underneath the model and prepares the data first. By cleaning and shaping the stream, it makes the downstream decision more stable and less sensitive to irrelevant variation. Noise filtering, smoothing, and normalization can make a chunk much easier to interpret. On the edge, that matters because every false alarm and every missed event wastes battery, attention, or bandwidth. That stream handling step sits at the foundation of a chapter. Once the data is framed correctly, the rest of the pipeline can move into pre-processing, feature fusion, task framing, and the later optimization choices. This is a practical engineering skill, not a theoretical detail. Poor window choices, low frame rates, or expensive overlap can make the input unusable long before the model gets a chance to help. The goal is to keep up with the stream while still preserving the events that matter. When that balance is right, the rest of the Edge AI pipeline has a real chance to work. Streams need a different kind of handling than documents because the data keeps arriving. The focus here is how visual evidence and real applications force us to think about timing, framing, and what a model actually gets to see. A stream is not a finished file waiting to be read from start to end. It is a live sequence of measurements, and each sample matters partly on its own and partly because of when it arrived. Edge devices have to deal with signals that never stop: temperature, vibration, audio, video, and more. Since they cannot hold or inspect everything forever, they need a way to break that flow into pieces a model can process reliably. Windowing gives the model a bounded input instead of an endless one. A chunk can be a few sensor values, a short audio slice, or a few video frames, but the goal is always the same: make the signal analyzable without losing its structure. Riverwatch Node shows the practical side of this idea. A low-power monitor watches for short events, and if the windows are chosen well, it catches the splash, the vibration, or the alarm-like sound. If they're chosen badly, the event never gets a fair chance to be seen. Timing controls whether the model has enough context, enough speed, and enough chances to see a short event before it disappears. These three terms set the basic trade-off in stream processing. Once they are in view, the rest of the design choices become much easier to reason about. A larger window gives the model more context, which helps when patterns unfold slowly or when you need to separate a real event from a brief fluctuation. The cost is more compute, more delay, and sometimes less clarity when details get blended together. Latency is about responsiveness. If gathering the window, running inference, and producing the result takes too long, the device misses the moment when action would still matter. A higher frame rate gives more chances to catch short-lived events, while a lower one saves compute but creates blind spots. That is why brief sounds, gestures, or bursts of motion can vanish if they happen between sparse windows. Overlapping windows helps because an event can appear in more than one frame, even if it starts at an awkward time. The trade-off is extra computation and scheduling pressure, so overlap buys coverage at the cost of cycles and energy. Those four ideas fit together cleanly. How much each frame contains, how fast a decision arrives, how many chances you get, and how much those chances share. That gives you a useful mental model for the whole problem. Video uses the same framing logic, even though each window may be just one image. The main question is still whether the stream is segmented in a way that lets the model catch the event before it passes by. A camera does not escape the stream problem just because the data looks visual. If sampling is too slow or the windows are too coarse, motion can be present in the scene but absent from the model's input. Those visuals are there to make the mechanics concrete. One frame shows a window taken from a stream, another shows how overlap changes coverage, and another shows what happens when the sampling rate is too low. The point is operational, not decorative. Before a model sees the data, signal processing can clean it up and make it more stable. That pre-processing often decides whether the downstream model gets a usable signal or a messy one. Filtering, smoothing, and resampling do not replace the model. They reduce noise and stabilize the input, so the model has less irrelevant variation to fight. On constrained devices, that can make the difference between steady behavior and wasted energy. When a short command or wildlife call gets missed, the failure may start long before classification. If the windows are too sparse, the model never had a fair chance to see the event at all. Edge engineers are deciding how to balance context, delay, coverage, and battery life. Those choices determine whether a low-power device can detect meaningful events without wasting computation. This is a practical design skill. The same trade-off shows up in audio keyword spotting, machine monitoring, safety cameras, wearables, and environmental sensing, where the system has to stay efficient and still remain reliable. Stream handling is part of the system's intelligence because it controls the evidence that reaches the model. Segment the stream well, and the rest of the pipeline can work with a fair view of the event. Segment it badly, and every downstream step starts from partial evidence. Digital signal processing is the step that shapes messy sensor data into something a model can actually use. The main ideas here are sample rate, filtering, and frequency views, because those are the tools that turn raw streams into reliable input on edge devices. Raw edge data rarely arrives in the right form for inference. Sensors drift, jitter, oversample, undersample, and collect noise, so DSP sits between the sensor and the model and reshapes that stream while while keeping power use under control. A stream monitoring node faces that question before it worries about model choice. If the input is too fast, too noisy, or too uneven, the first job is to reshape the signal so the model sees the important parts instead of the clutter. Sample rate is not fixed by nature. It is chosen for the job. The right rate depends on how much detail the application needs and how much storage, bandwidth, and compute the device can afford. A sample rate tells you how many measurements arrive each second. Slow changes can be tracked with fewer samples, but brief events like a cough, a bird call, or a vibration spike can disappear if the rate is too low, so higher rates give detail at the cost of more work. Edge systems often have to adapt because the sensor and the model were not built with the same constraints. A device may record quickly to preserve evidence, then reduce the rate before inference, unless the event is short and easy to miss, in which case the higher rate has to stay. Downsampling reduces the amount of data, which is attractive on constrained hardware, but it has to be done carefully. The main danger is aliasing, where fast changes get misread as slower ones after the rate is reduced. Reducing the sample rate can make the whole pipeline lighter. If the node processes half as much data, it often saves power and responds faster, which matters when the device has a tight energy budget. Aliasing happens when high-frequency content is still present and the data rate drops too far. The safe pattern is to filter out frequencies the lower rate signal cannot represent, then downsample so the model does not see a fake pattern that never existed. Upsampling moves the other way by creating extra samples so streams can be aligned. It is useful when different sensors run at different rates, but it only estimates missing points. It does not restore information that was never captured. Multi-sensor systems often need one fast stream and one slow stream to meet in the middle. Adding samples lets those streams line up for comparison or fusion, which is useful in systems like building monitors or fitness trackers. Interpolation fills gaps with plausible values, so it is excellent for synchronization. It cannot invent a short event that the sensor missed, which is why upsampling helps alignment, but not data recovery. Once the rate is under control, filtering becomes the next major tool. Different filters keep different parts of the signal, so they can smooth noise, remove drift, or isolate the band that matters to the model. A low-pass filter keeps slow changes and removes rapid ones, which helps with smoothing and downsampling. A high-pass filter does the opposite, while a bandpass filter keeps only a chosen frequency range. Even a moving average can be valuable because it is cheap and effective on small devices. Filtering is not only for cleanup. A low-pass filter can reveal a trend hidden under sensor chatter, while a high-pass filter can expose impacts or abrupt changes. So the filter can act like a lens as well as a broom. Speech-like and audio-like signals often need a narrower focus. A bandpass filter keeps the useful frequency band and rejects the rest, which reduces the burden on the classifier and makes it less sensitive to background noise. The same pre-processing ideas show up in images too. Cameras may produce frames that are too large, poorly aligned, or full of irrelevant detail. So the model still needs the input reshaped before inference can begin. Cropping and resizing are practical steps when the model expects a fixed shape. They remove extra border area, standardize geometry, and keep the device from wasting cycles on a frame that does not fit the network. Image filters behave the same way they do in audio. A low-pass filter softens fine detail, while a high-pass filter emphasizes sharp transitions, so the model sees either smoother regions or clearer edges depending on the task. Feature detection goes one step beyond filtering by turning raw pixels into compact structure. Edges, corners, blobs, and ridges often summarize the important geometry of scene better than the full image does, which is valuable on constrained devices. Some signals only make sense once they are transformed. The frequency view can expose structure that is hard to spot in raw samples, especially when a vibration or audio trace looks like noise at first glance. In the time domain, the signal is tracked sample by sample. In the frequency domain, the question changes to which frequencies are present and how strong they are, and that can reveal a hidden pattern that a lightweight model can use. Spectral analysis uses Fourier-style transforms to describe a signal by frequency. A spectrogram is especially useful because it shows how frequency content changes over time, turning subtle audio or vibration patterns into shapes that are easier to classify. A practical edge pipeline may never send raw samples straight to inference. It can first downsample, filter, and build a spectrogram-like representation, then let a small model decide whether the pattern is worth an alert. These pre-processing choices are a core edge skill because they change what the model can afford to see. Good DSP helps smaller models run on cheaper hardware with less power, less noise, and better latency. Engineers who understand pre-processing can make constrained systems behave far better without changing the model itself. Trimming unnecessary samples, removing noise, and keeping the pipeline lean all translate into lower power use and more reliable inference. The hard part is restraint. Too little pre-processing leaves the model buried in clutter, but too much damages the signal before the model can learn from it. So the goal is a narrow middle ground where the data stays faithful and still manageable. Digital signal processing gives edge systems a way to reshape raw sensor data before inference begins. The focus here is on the practical tools that make a stream usable. Rate changes, filtering, and transforms that reveal structure the model can work with. Edge sensors almost never produce data in the exact form a model wants. The first task is to make the stream usable by handling its rate, shape, noise, and timing before any prediction starts. That bridge matters because a model can only reason well when the input already fits the problem. Without pre-processing, the inference step spends its effort fighting the signal instead of learning from it. Resampling adjusts a signal's effective rate, so it fits the device and the classifier. The main idea is to keep the useful structure while making the stream easier to process. When samples arrive faster than the hardware can analyze them, processing every one is wasteful. Resampling reduces that mismatch, so the system spends its compute on the pattern, not on near duplicates. A reduced rate signal can distort high-frequency content if that energy is left in place. The safe approach is to filter first, then lower the rate, so the model does not mistake folded frequencies for real structure. Upsampling solves a different mismatch. Two signals may need a common rate before features can be combined. Interpolation fills gaps to create alignment, but it does not invent new information. So timing still has to be chosen carefully for short events like commands or speech. Vision has the same problem, only with height, width, and aspect ratio instead of sample rate. The input has to be reshaped so the model sees a valid image without losing the evidence that matters. A resize can preserve more of the scene, a crop can focus attention, and a squash can force the image into a fixed frame. Each choice trades detail, geometry, and convenience, so the right one depends on what the task must preserve. On a low-power device, image shaping is also a capacity problem. The pipeline has to fit the compute budget while protecting the parts of the scene that carry the signal for detection or classification. Filtering is the most direct way to clean up a stream for a specific task. Different filter types keep different parts of the signal, so the choice depends on what the model needs to notice. A low-pass filter preserves slower changes. A high-pass filter emphasizes rapid changes, and a bandpass filter keeps only a middle range. That gives you control over which parts of the signal survive and which parts get suppressed. Real sensor data often mixes useful information with noise from the environment and the hardware itself. A good filter can separate speech from fan noise, or smooth a trend when stability matters, or sharpen transitions when sudden change is the important cue. The algorithm is only half the story. The hardware matters too. If the device has optimized libraries or dedicated accelerators, common transforms become practical choices, and that changes the trade-off between latency, power, and clarity. Frequency space makes hidden structure easier to spot. The goal is to turn a complicated waveform into something that exposes repeating patterns, tones, and bursts more clearly. A waveform can be described either by how it changes over time or by how its energy is distributed across frequencies. The Fourier transform is the bridge between those two views, and it sets up the spectrogram as a useful representation for edge AI. A spectrogram spreads the signal across time and frequency, so structure becomes visible instead of buried in a single line. Short commands, machine tones, wildlife calls, and vibration events often separate more cleanly once the energy is laid out this way. For Riverwatch Node, the stream does not need to stay in raw form forever. It can be resampled, cleaned up, and converted into a compact visual input like a spectrogram before the classifier makes its decision. Some edge vision tasks do not need a deep network to discover everything from pixels. Classic features reduce the scene to a smaller set of useful structures, which is easier to process on limited hardware. Edges mark boundaries, corners mark directional change, blobs capture local regions, and ridges trace elongated shapes. Those descriptors turn a dense image into a smaller description that a lightweight system can reason over more cheaply. The contour view shows why feature extraction helps. Once the scene is reduced to structure, analysis gets simpler. Smoothing removes distracting variation, while sharpening pulls boundaries forward, and both can make the important parts easier to detect. Interviewers ask about these topics because they test whether someone can shape inputs to fit real devices. A strong edge engineer knows when to preserve a signal, when to simplify it, and when to transform it so the system stays within its latency and power limits. Feature design and sensor fusion are the core skills here, because edge models are only as good as the inputs they receive. The goal is to shape raw signals into something ordered, trustworthy, and useful before inference starts. A streaming sensor does not give the model a clean decision each time a sample arrives. The signal has to be condensed into features that are compact, ordered, and reliable enough for the model to act on. The first version of this problem stays inside a single sensor path. That makes the idea easier to see because the model is not yet dealing with multiple sources, only multiple views of the same signal. A single sensor can produce several derived signals, and each one highlights a different part of the same process. One feature can track slow drift, another can capture sudden change, and another can measure variability so the model can separate signal from jitter. That stacking often gives the first practical improvement, because each feature contributes a different clue. The goal is diversity without chaos. Enough information to help the model, but not so much noise that the input becomes hard to learn from. Order matters because the model reads the feature vector position by position. If the positions change later, the same numbers no longer mean the same thing. And on an edge device, every extra feature also costs time and memory. Once the input comes from more than one source, the same thinking becomes sensor fusion. The question shifts from combining features within one stream to combining sensors so the system can make a better local decision. Fusion brings together data from different sensors so the model can see the situation from more than one angle. A river node, for example, might combine water quality, vibration, and temperature. A wearable might combine motion and heart rate. A building controller might combine occupancy and HVAC feedback. These combinations usually fall into a few practical patterns. The pattern tells you whether the extra sensor adds breadth, redundancy, or a new observable that neither source can provide alone. Complementary fusion joins signals that describe different sides of the same situation. One sensor may reveal flow changes while another reveals temperature, and together they produce a more complete picture than either one alone. Competitive fusion is useful when sensors overlap in purpose. The system can compare them and lean on the more trustworthy source if one drifts or fails, which is why duplicate probes are so valuable in critical settings. Cooperative fusion combines sources in a way that creates a new kind of information. Stereo vision is the clean example. Depth appears because two viewpoints are interpreted together, not because either camera could measure depth alone. These labels are practical because they guide design choices. They help you decide whether a sensor is adding breadth, redundancy, or a genuinely new observable, and that affects how you pre-process and trust it. Fusion only works when the sources line up cleanly. The three steps that matter most are aligning time, matching scale, and then combining the values into one representation. If the streams are misaligned, the combination becomes misleading instead of helpful. Before any model sees the data, the sources need to refer to comparable moments and compatible numeric ranges. Time alignment means the measurements should describe the same instant or moments close enough to compare. When sampling rates differ, the slower stream often needs resampling so the model is not handed a false pair of values from two different times. Different sensors often live on very different scales, and large numbers can dominate a model even when they are not the most informative. Normalization pulls the features onto a comparable scale so the model can use meaning rather than raw magnitude. Clipping can protect the fused representation from occasional spikes that would otherwise distort it. The trade-off is important. If the threshold is too tight, the very anomaly you want to detect gets flattened away. The Riverwatch example makes the sequence concrete. Water quality data and vibration data need to line up in time, sit on comparable scales, and then enter the model as one combined input structure so neither sensor overwhelms the other. There is no single correct place to fuse signals. Sometimes raw channels should meet early, and other times each stream should be cleaned or transformed first before the combination happens. Early fusion can work when the raw inputs together form a clearer picture. Late fusion can work when each stream benefits from its own filtering or feature extraction first, and the right choice depends on the problem and the model's tolerance for complexity. The order is less important than preserving meaning. Whether you smooth first or fuse first, the timing and scale of the inputs must stay compatible so downstream inference is not corrupted. This becomes a deployment skill, not just a modeling skill. At the edge, the real challenge is often shaping signals well enough that the model can be trusted under real constraints. Jobs in IoT, wearables, industrial monitoring, and robotics depend on input quality as much as on architecture choice. Engineers who can reason about latency, scaling, and sensor reliability are valuable because those systems fail when the inputs are weak. The practical lesson is that raw sensor data usually needs shaping before a model can trust it. Better edge systems come from better inputs, and good fusion improves stability as well as accuracy. once the features are combined and the sensors are aligned and scaled, the next question is which algorithm family should use that input. The device-side implementation then has to respect the same constraints on timing, memory, and reliability. Combining sensor signals starts with the practical problem of turning messy measurements into something a model can trust. The focus here is alignment, scale, and the choice of how different inputs should meet before inference. Raw data is rarely ready to use on its own. The work is to reshape those streams into inputs that line up in time and behave consistently enough for the model to interpret. The first discipline is choosing only the signals that matter and making them comparable. On edge devices, that matters even more because readings arrive at different rates, can be missing, and can drift far outside the range you saw during testing. That order gives you a workable pipeline. First, bring the timing into shape, then smooth obvious noise if needed. Then put the features on a common scale, and only after that merge them into the vector that reaches the model. The same pipeline can support two different ideas. One sensor can produce several useful features, or several sensors can contribute evidence toward one decision. And both cases depend on careful preparation before fusion. A single vibration signal can be turned into multiple views of the same motion, such as average level, short-term variation, and peak spread. Those derived features often tell the model more than the raw waveform alone because each one highlights a different property of the same source. Fusion across sensors goes one step further. Accelerometer, gyroscope, and heart rate data can reinforce each other. So the model sees complementary evidence instead of relying on a single channel that might be incomplete or misleading. Different fusion patterns serve different goals. Some inputs describe different sides of the same event. Some compete to estimate the same event, and some only make sense when the joint pattern is considered together. The implementation should match that structure instead of forcing every case into the same mold. On small hardware, the sequence of operations matters because mistakes in timing or scale are hard to recover from later. The safest path is to align first, then transform, then normalize, then combine. Time alignment comes first because two sensors may never report at the same instant. If you combine mismatched timestamps, the math may look clean while the physical pairing is wrong, which makes the fused input unreliable from start. Once the signals line up, put them on compatible scales. A large numeric range can dominate a smaller but more informative one, so a simple scaling step keeps the channels comparable before they are merged. Clipping is a defensive layer for real hardware. When a reading spikes or goes malformed, clipping can prevent one bad value from corrupting the whole feature vector, even though the sensor still needs investigation later. A compact example makes the workflow easier to picture. Riverwatch Node shows how a small device can turn raw sensing into a stable local decision by combining features, timing, and environmental context. Picture a low-power river monitor that does not forward every raw sample. It extracts a few useful features from a stream, adds nearby context such as temperature or rainfall, and then cleans the inputs so the local classifier sees one compact, trustworthy vector. Small devices cannot afford to process endless raw signals at full fidelity. They need a disciplined way to compress what matters so the model can act quickly and reliably on the device itself. This connects directly to deployment work in embedded, IoT, and robotic settings. The valuable skill is often not just model choice, but the ability to make messy sensor data fit the constraints of a real system. Real systems fail at the seams. Timestamps drift, values go missing, units disagree, and noise leaks through. The engineer who can clean up those seams and produce stable inputs is often more useful than someone who only tunes a classifier after deployment. The practical goal is to transform mismatched readings into an input vector the model can actually use. The best fusion choice is the one that preserves timing, respects scale, survives bad inputs, and fits the device that has to run it. Algorithm choice starts with the job the system has to do. The useful mental map for edge AI comes from the function classify, estimate, detect, group, reduce, or transform. That shift prevents a common mistake, trying to force a real sensing problem into a favorite technique. When the function comes first, the algorithm family becomes much easier to choose. A stream monitor usually has more than one task at once. It may clean signals, watch for unusual behavior, decide whether something matters, and prepare data for upstream systems, so multiple algorithm families work together in one pipeline. Classification handles discrete choices. The goal is to place an input into one of a fixed set of labels, which makes it the right fit when the answer has to be a category rather than a measured value. Binary cases are yes or no decisions, while multi-class and multi-label problems expand that idea to several possible labels. In a sensing system, that might mean deciding whether a person is present, whether an animal appears in frame, or which condition best describes a stream segment. The key distinction is that classification ends in a label. If the output must land in one bucket or several predefined buckets, the problem belongs in this family rather than in a numeric one. Regression is the matching idea when the device needs a number. Instead of choosing among labels, the model estimates a continuous value that can drive control logic or analysis. Temperature, pressure, speed, vibration, and humidity all fit this pattern. A virtual sensor often uses regression because it infers a quantity from related signals when that quantity is not measured directly. On a river monitor, that number might be flow rate from water level and current readings, or a concentration inferred from cheaper proxy sensors. The output matters because it feeds something downstream, not because it belongs to a class. Image and video tasks often need spatial understanding as well as recognition. The question becomes not only what is present, but where it is and how much of it matters. Object detection identifies discrete things and places them in the frame, usually with boxes or similar markers. That is the right fit when the system needs to count or localize objects such as people, vehicles, or animals. Pose estimation goes deeper than presence. It tracks body structure, which makes it useful when posture, balance, or motion quality matters more than a simple object count. Segmentation is about precise regions. When boundaries matter, a box is not enough. so the model assigns labels to the pixels that belong to each object or surface. Anomaly detection asks a different question from classification. The focus is whether a signal has drifted away from normal behavior, which is especially useful when failures are rare or labels are incomplete. A current spike, a drifting calibration, or an unusual vibration pattern all count as departures from expected behavior. At the edge, that matters because the device is close to the process and can react before the problem grows. For a river monitor, that could mean sensor drift, a strange temperature pattern, or a pump event that breaks the usual rhythm. The strength of this approach is that it can still work when examples of failure are scarce. Clustering organizes data by similarity instead of by preset labels. It is useful when the system is trying to discover structure in repeated patterns or group things that behave alike. That makes it a good fit for environments that are still being understood. Repeated HVAC cycles, recurring sounds, or call signatures can all be grouped so later analysis has a cleaner view of the data. The two ideas overlap, but they are not the same. Clustering says which inputs belong together, while anomaly detection says which input falls outside the normal set of behavior. Dimensionality reduction makes data smaller and easier to work with while keeping the important meaning. It often helps when raw inputs are large, noisy, or expensive to compare directly. A long audio clip can become an embedding, a face can become a compact vector, and sensor traces can be mapped into a smaller space. That smaller space makes comparison and pattern matching cheaper. This family is often part of the pipeline rather than the final goal. In a river system, a compact history of several sensors can make later classification or clustering more stable and efficient. Transformation covers algorithms that convert one signal into another useful form. The emphasis is on changing the representation so the next stage has better input to work with. Noise removal is one common case, but the idea is broader than denoising. Speech can become text, a weak image can be sharpened, or a raw signal can be reshaped into something easier to interpret. A transformation can happen before classification or after a prediction when results need cleanup or post-processing. The job is to convert data into the form that the next step needs. Real-edge systems rarely use just one family. The practical skill is combining the right pieces so they fit the sensing job and the resource limits at the same time. A river node might clean readings, compress history, classify events, and watch for anomalies all at once. A camera pipeline can detect objects, segment regions, and refine the result before anything is sent onward. That translation is what employers care about. When the function is framed correctly, the implementation becomes much easier to narrow. When it is framed badly, even a strong model can solve the wrong problem. That map is the fastest way to reason about algorithm choice. Edge systems usually stitch several of these families into one pipeline, and that composition is often what makes the system work at all. Algorithm families become much easier to recognize when you sort them by the job they do. The outputs tell you a lot about the problem, and that is the quickest way to choose a useful model family. The outside view starts with input and output, not internals. That perspective helps you match a real task to the right family before you spend time comparing architectures. A functional view asks a simple question: what does the system receive, and what does it produce? Once you think that way, the shape of the answer often points straight to the algorithm family you need. Those figures are useful because they show behavior, not hidden internals. A score, a box, a mask, or a cluster layout each signals a different kind of problem, and that visual cue is often enough to narrow the choice quickly. The main families differ by the form of their output. Each one answers a different kind of question about the data, which makes the task easier to identify from the result alone. Classification is the family to think about when the answer should be a category. The question is not how much or where, but which bucket the input belongs in. Classification produces one label or several labels, depending on a task. The probabilities are useful too, because they show how strongly the model favors one class over the others. A sensor stream like that fits classification well because the system is choosing among a small set of known states. The raw signals stay continuous, but the final decision becomes a discrete event that another system can use right away. Regression applies when the answer should be a number rather than a category. The output might estimate a measurement, a remaining life value, or some other continuous quantity. That family is useful whenever a device has to infer a value that is missing, unavailable, or too costly to measure directly. In edge systems, that often becomes a virtual sensor problem. For Riverwatch node, the output could be a flow estimate or a prediction of how the level will change. The important clue is that the result is continuous, so the model is answering with magnitude, not membership. Spatial tasks add location to the answer. Now the question is not only what is present, but where it appears and, sometimes, what shape it has. Detection marks approximate position with boxes and usually attaches a label and confidence. That makes it different from plain classification because the model is naming each instance and locating it in the frame. Pose estimation pushes the output toward key points such as joints or landmarks, while segmentation labels pixels or regions directly. Those outputs look different on the board, and that difference tells you exactly how much spatial detail the application needs. Anomaly detection look for behavior that falls outside the normal pattern. That makes it especially useful when the event is rare, drifting, or not fully known ahead of time. A stream, machine, or sensor can all become anomaly problems when ordinary behavior is the reference point. The model learns the baseline first, then watches for sequences that stop resembling it. The output is often a score or alert rather than a fixed class label. That matters because the system is not naming a known category. It is warning that the current pattern does not belong. Clustering groups inputs by similarity without needing labels in advance. It is useful when the system has to discover structure instead of matching a predefined list of classes. That makes clustering a good fit for local pattern discovery on the edge. The device can organize behavior into groups even before anyone has named those groups by hand. The visual clue is a set of items arranged by resemblance, not a class chart or a box overlay. In practice, those groups can help reveal operating modes or simplify later decisions. Dimensionality reduction changes the representation itself. The goal is to keep the useful structure while making the data smaller, faster to compare, and easier to work with. On constrained devices, that compact form can save storage and computation. It also helps when features need to be visualized or passed into another algorithm downstream. The output here is a condensed version of the input, not a decision about the world. That reduced form often feeds clustering, retrieval, anomaly detection, or classification more efficiently than the original data could. Transformation maps one signal into another signal. That can mean cleaning, filtering, enhancing, or converting data into a form that later stages can use more reliably. A raw waveform might become a cleaner waveform, or speech might become text. The common idea is that the system is reshaping the data rather than deciding what category it belongs to. This family is easy to miss because it often sits before the visible task. Yet a good transformation step can be the difference between a noisy stream that fails and a stable one that the rest of the pipeline can handle. The same data stream can support several different outputs, depending on the goal. That is why these families are best treated as functional views of a problem, not rigid boxes. The Riverwatch example can produce a label, a number, an anomaly flag, or a clean signal. Each answer serves a different purpose, even though the input sensors are the same. That difference is design flexibility, not redundancy. A dashboard alert, a maintenance estimate, and a denoise stream are not interchangeable because each one supports a different decision. Vision systems do the same thing. Detection, segmentation, pose estimation, and post-processing can all appear in one pipeline, and the output shape tells you which task matters most. Recognizing the family from the output saves time in design and debugging. It helps you choose a better first model, avoid the wrong problem framing, and move faster on constrained hardware. An engineer who can identify whether the job needs classification, localization, anomaly detection, or a transformation step can make better decisions earlier. That skill matters as much in a prototype as it does in a production device with tight limits. A quick rule helps when the problem is still fuzzy. Start from the kind of output the application needs, and the relevant family usually becomes much easier to see. A discrete label points to classification, a number points to regression, and location points to detection, pose estimation, or segmentation. Deviation suggests anomaly detection. Groups suggest clustering. Compression suggests dimensionality reduction. And conversion suggests transformation. If the system needs several of these, they can be chained into one pipeline. Real edge systems usually combine several functions rather than relying on one model alone. The best path is the one where input, output, and operational goal all line up cleanly. Implementation style is the first practical choice that decides whether an edge AI idea can run on real hardware. The point here is to separate the kind of task from the kind of implementation, because that choice shapes cost, speed, and reliability. The first question defines the behavior you want, but the second question decides whether the device can actually carry it out. On a small node, a good action still fails if it is too slow, too expensive, or too power-hungry to survive in the field. The same sensing problem can be solved with a hand-coded rule, a classical model, or a deep network. At the edge, that choice turns into a budget question: memory, latency, power, maintainability, and how easily the system can be updated. Heuristics are the simplest form of edge implementation, and they work best when the problem is narrow and well understood. The advantage is speed and clarity. The risk is that the logic can become fragile when the environment gets more complex. A heuristic encodes human judgment directly into a rule. That kind of logic is ideal when the signal is clean and the action is obvious, because the device does not need to infer much. It only needs to check whether the condition has been met. That makes heuristics useful for small edge jobs like threshold alarms and simple feature checks. Once pre-processing has turned raw data into a meaningful feature, a rule can interpret the result with very little compute. The trouble starts when the system has too many variables or too many special cases. The rule set grows branch by branch until it becomes hard to test, hard to maintain, and easy to break when the environment changes. Classical machine learning sits between manual rules and deep learning. It learns patterns from examples, which gives you more flexibility than a fixed heuristic without demanding the full complexity of a neural network. The training phase is where the model adjusts its parameters from data, and inference is where it applies what it learned to live inputs. That split matters at the edge because training can happen elsewhere, while inference has to fit the device. A decision tree, logistic regression, or random forest can be a strong fit when features are already engineered. In that setting, classical ML gives a practical middle ground for teams that need usable predictions without the cost of a larger model. These models often move across hardware more easily than heavier neural networks, which is a real advantage on diverse devices. The trade-off is that they rely on the quality of the input features, so they struggle more when the raw signal is noisy or poorly shaped. In workflows that involve audits, human review, or sensitive decisions, explanation can be more valuable than a tiny accuracy boost. Classical ML often helps there because engineers can sometimes trace why the model raised a flag. A useful hybrid approach is to borrow a pre-trained model for representation and attach a lightweight classifier on top. That reduces the amount of labeled data and training time, which is especially helpful when field data is scarce. A cascade saves power by reserving expensive computation for the moments that matter. The first stage watches continuously, and only after it detects a likely event does the larger model analyze the full input. Deep learning gives the widest range of behavior because it can learn directly from raw, complex input. That flexibility is useful when manual features stop being enough, but it comes with a heavier cost in compute, memory, and data. When the data is messy or highly structured, deep models can discover patterns that hand-coded logic misses. That is why they become attractive for images, variable sound, and other inputs where the shape of the signal matters. The price of that flexibility is that the model usually needs more examples, more memory, and more runtime support. A small device can still run one, but only if the hardware, power budget, and update path are designed for it. Different model families fit different input structures. Feature-based models work well on fixed summaries, while convolutional models are better when local relationships in space or time matter. So the best choice is the one that matches the data you actually have. The practical rule for edge systems is to start with the simplest method that still meets the requirement. That keeps the design small, understandable, and easier to support when the device is deployed in the real world. If a rule is enough, keep the rule. If the problem needs a learned model, choose the smallest model family that can handle the variability and only move to deep learning when the simpler options fail. That mindset is valuable in design reviews because it shows judgment, not just ambition. Strong engineers can defend why a threshold is sufficient in one case and why it would be unsafe in another, while still respecting latency, memory, and maintainability. For the Riverwatch node, the path is straightforward. Begin with a derived feature rule if the signal is stable. Move to classical ML when the environment becomes noisier, and use deep learning only when the pattern is too rich for shallow features. The right method is the one that still fits the device before the field conditions force a redesign. The key idea in this function is the combination of a threshold and persistence. The input checks at the top protect the device from bad values, and the final return line shows the actual heuristic. The derived feature must be high enough, and it must stay high for several readings before the alarm fires. That example is deliberately plain because the point is the decision, not the sophistication. Many edge devices need exactly this kind of small, reliable judgment call, and the implementation style determines how far the system can go before it stops being practical. Implementation style changes what an edge algorithm can do in practice. The same task can be built as rules, a train model, or a compact neural network, and that choice affects speed, memory, and how easy the system is to trust. Algorithm choice is not only about the task itself. It is also about the form the decision takes inside the device, because that form controls cost, clarity, and deployment risk. A system can detect danger in several ways. With hand-coded conditionals, with a classical model trained from data, or with a small neural network. On the edge, those choices change memory use, latency, portability, explainability, and how much auditing effort the field team needs. Functionality asks what decision the system makes, while implementation asks what machinery produces that decision. The same alarm or control action can be built from explicit rules or learned parameters, and that difference matters when the code has to run on a small device. A conditional is the simplest decision mechanism available. It may look plain, but when a measured value must directly trigger a safe action, that simple logic can carry real practical intelligence. An if statement compares a sensor reading to a condition and then chooses an action. On embedded hardware, that can be enough when the goal is a reliable response rather than a complex inference pipeline. That kind of logic is easy to inspect because every decision path is visible. Rule-based code stays popular in embedded systems for the same reason. It is cheap to run, straightforward to test, and predictable under tight hardware limits. A braking system shows the whole loop in miniature. It measures distance, estimates time to impact, compares that estimate to a safety threshold, and then decides whether braking is necessary. Thresholding is the first step. A computed value is compared against a boundary. That gives the system a clean yes or no decision point, which is useful whenever the signal can be reduced to a margin. Classification follows from that comparison. The situation gets assigned to one of two states, and that label becomes the basis for the rest of the response. Rule-based control connects the label to an action. Once the system decides the situation is unsafe, the code can immediately choose the response that protects the device or the person using it. That small chain is already a complete edge decision loop. The important question is not how fancy the code looks, but whether the decision matches the situation well enough to be trusted. The key idea sits in the comparison near the end. The code turns a distance and speed reading into time remaining, then checks whether that time is below the stopping requirement plus a safety margin. If it is, braking is triggered. The domain knowledge is visible in the variables and the threshold. A person chose the safety margin, a person chose the cutoff, and a person tied that judgment to the action, which is exactly how heuristics make small devices behave consistently. Heuristics are handcrafted rules that work well when the problem is narrow and the engineer can state the decision in plain language. They are the bridge between practical knowledge and a device that needs to act without heavy computation. That style works well when the rule can be stated clearly. If a signal stays high, take action. If a pattern is missing, suppress the alert. If two conditions must both hold, require both. The strength comes from the fact that the rule matches the engineer's understanding of the domain. Those properties make heuristics attractive on edge devices. A sensor node can watch for turbidity above a safe band, wait for several readings to confirm it, and then send only the event instead of streaming everything upstream. The weakness appears when the rule set grows. Once several inputs interact, the number of cases expands quickly, and a rule that made sense alone can behave badly when combined with others. Learned models shift the decision boundary from hand coding to data-driven training. That changes where the intelligence comes from, and it opens the door to patterns that simple rules cannot capture well. Classical machine learning uses examples to infer the boundary from features instead of writing it directly. Deep learning goes further by learning much of the feature construction too, which reduces how much has to be handcrafted before training starts. That added flexibility comes with cost. Learned models need data, tuning, evaluation, and careful deployment, and they may demand more compute and memory than a simple rule set can afford on the target device. Embedded work forces every decision through the limits of the hardware. The engineer has to translate a real requirement into deterministic behavior, then choose the simplest implementation that still meets the safety and reliability target. A requirement like warning before damage or braking before impact has to become something a real device can execute every time. That means proving the behavior is reliable under memory, timing, and power constraints, not just correct on paper. A tiny snippet can hold a useful judgment when it is placed in the right context. The intelligence comes from making the right decision at the right point in the system, not from making the code look elaborate. A simple if statement is a valid AI implementation when the rules are known and the task is narrow. Once the inputs get messy or the environment stops matching the heuristic, the hand-coded approach runs out of room and the implementation style has to change. Edge optimization starts with a hard constraint. The device decides what is even possible. The point of this part is to connect model design to memory, latency, and energy, because a good offline model can still fail on real hardware. A model does not get judged in isolation. It gets judged inside the machine that must run it. That means the hardware limits shape every later choice, from architecture to pre-processing. On the edge, accuracy alone is never enough. The model has to fit the available RAM and flash, respond within the latency budget, and keep power use low enough for real operation, or it fails even if the test score looks good. Those two kinds of performance pull in different directions. A larger model may make better predictions, but if it blows the memory budget or drains the battery, it is not a usable solution. A smaller one may run easily and still miss the rare event that matters. That changes the question from can we optimize to which optimization preserves usefulness? The right answer depends on what the device can support and what failure would cost in deployment. Riverwatch node makes the distinction concrete. A tiny model can still be the wrong solution if the whole sensing and inference path is too heavy for a low-power device to keep running in the field. The goal is not to process every sample at full fidelity. The node only needs to catch important events, report them fast, and survive long enough to keep monitoring. A small classifier is not automatically cheap when it sits behind smoothing, windowing, and feature extraction. In many edge systems, the hidden cost is the signal processing needed to make the input usable, and that can dominate compute, memory traffic, and time. The better comparison is the whole pipeline against the whole payoff. Sometimes that means simpler features or less data. Sometimes it means a classical model. Sometimes a small neural network or a hardware-accelerated operator is the best fit, but only if the device can actually exploit it. Algorithm family matters because each one has its own memory shape and runtime shape. The fit between the model and the chip often matters more than the label attached to the algorithm. Classical models often use less memory and less compute than deep learning, especially when the input is already clean and structured. But a light model can become expensive if the feature pipeline is complicated, while a compact neural model can win end-to-end by replacing hand-built preprocessing. So device-aware design is broader than picking a model. You can shrink the input, lower the sampling rate, simplify features, or choose an architecture that matches the chip. Often the biggest gain comes from removing work before inference starts. Some improvements keep the math the same and only change how efficiently the system executes. These are the optimizations that improve fit without changing the model's meaning. Operator fusion is a good example. Adjacent operations can sometimes be combined into one faster pass, so the runtime moves less data and spends less time between steps. The catch is that the framework has to recognize the pattern and the hardware has to support the efficient execution path. Hardware acceleration works the same way. Quantized inference, vector instructions, or a neural accelerator can turn an ordinary model into something practical, because the gain comes from the pairing of software and device, not from the model alone. Other techniques change the model itself, so the efficiency gain comes with an accuracy trade-off. The important question is not whether compression helps, but how much behavior it preserves. Quantization lowers numerical precision. Pruning removes less important structure, and distillation trains a smaller student to imitate a larger teacher. Binary neural networks push precision even lower, while spiking networks use a different computation style that can be efficient on the right hardware. These methods are useful, but they are not interchangeable and they are not free. A compressed model can keep similar headline metrics while still shifting behavior at the edges. Rare classes, noisy inputs, borderline cases, and underrepresented groups often feel the loss first. Compression should be treated as one step in the design process, not the end of it. Start with a model that fits the device, then compress if the trade makes sense, and judge the result by the full set of costs and risks, not just a single benchmark number. Riverwatch shows the disciplined path. Keep the pipeline lean and make the whole system survive in the field. Wearables show the warning. Compression can look safe on average while quietly hurting the people or cases that are hardest to model. A compressed health wearable may keep respectable overall accuracy and still fail for a minority subgroup. Average performance can hide that kind of damage, so a small model is not automatically a fair or reliable one. That failure often starts with imbalance that was already present in training. If a subgroup had less representation to begin with, lossy optimization can erase the little margin that was protecting its performance. The evaluation rule is simple. Inspect subgroup behavior, long-tail cases, and the edge conditions that matter to deployment. Efficiency is only a success when the model stays dependable for the cases that count, not just for the average one. That is the skill gap between leaderboard chasing and real deployment work. Strong edge practice means reasoning about memory, latency, energy, and accuracy together, then defending that choice in hardware-aware terms. Deployment work demands choices that match real devices, plus the judgment to know when compression helps and when it creates risk. The explanation has to connect performance numbers to the limits of the machine, not treat those limits as an afterthought. The best edge system is not the smallest one possible. It is the one that fits the device as a whole, preserves the behavior that matters, and stays trustworthy when the inputs stop looking average. Edge optimization is about making a model fit the device's real limits: memory, latency, battery, and reliability. The central question is not only whether the model works, but whether it works under field constraints. Riverwatch Node has to adapt to its hardware, not the other way around. That framing matters because every later choice has to respect the device's battery, memory, and runtime limits. At the edge, the environment is fixed and often harsh. A model may be accurate, but if it cannot stay within RAM, ROM, timing, and energy limits, it will fail in practice before it ever proves useful. A model that feels ordinary in the cloud can become too expensive on a small processor. Extra milliseconds, extra memory, or extra power draw can turn into missed events, overheating, or a dead battery. Choosing an algorithm already commits you to a hardware profile. The model family, the runtime support, and the device's instruction set all shape whether the system will actually be deployable. Smaller classical models are often easier to ship when the features are strong and the task is simple. Compact, deep models can be more accurate on richer signals, but they usually need more memory, more tuning, and better runtime support. Pre-processing belongs in the cost calculation too. If the device spends most of its energy extracting features before prediction even starts, a cheap classifier can still be expensive to run. It helps to separate optimization by what it changes. Some methods preserve behavior, some accept a quality trade-off, and some only work when the hardware stack supports them. The useful lens is the effect on deployment. That keeps the discussion tied to latency, memory, and compatibility instead of treating optimization as an abstract technique. Lossless speedups improve execution without changing the intended prediction. They depend on support from the compiler, runtime, or hardware, so the same idea may be available on one stack and impossible on another. Lossy methods reduce size or speed up inference by giving up some representational detail. Quantization and pruning can be worth it, but they may shift errors toward rare cases or underrepresented conditions. Some optimizations only pay off when the device, compiler, and operators line up. A smaller graph can still be operationally difficult if it depends on a special accelerator path or a narrow library version. The risky part is that headline metrics can hide the real change. A model may keep a strong average score while becoming worse on the cases that matter most. Compression can preserve overall accuracy and still damage the error pattern underneath it. That often shows up as weaker rare event detection, worse borderline decisions, or uneven performance across locations and groups. A compressed model needs to be judged as a new system. The real question is which cases moved and who absorbs the cost when those cases fail. Riverwatch node is a deployment trade-off, not a benchmark exercise. The right choice balances accuracy, battery life, and whether the device can actually execute the model cleanly in the field. A larger model may perform well, but drain the battery too quickly. A smaller model can extend life, yet it may need quantization or operator fusion if the device lacks floating point support or fast enough inference paths. The practical goal is mission continuity under actual device limits. The elegant model is not the right answer if it cannot survive the operating conditions reliably. Product and deployment roles expect this kind of thinking. Performance, memory, latency, and energy all have to be balanced without quietly degrading service quality. Shrinking a model is only one part of the job. The device still has to meet memory and timing targets, stay within power limits, and avoid introducing new compatibility problems. A model becomes product ready when it fits the hardware, survives real operating conditions, and still serves the cases that matter most. Accuracy alone does not finish the job. The last check is where many optimizations are judged honestly. Once the model is compressed, the evaluation has to widen again to catch rare failures and subgroup effects. Rare species, minority physiology, noisy sensors, and seasonal edge cases can be the first things to degrade. If those cases matter to the mission, a small compression gain may hide a serious loss of reliability. Optimization is not automatically dangerous, but it always changes the risk profile. The job is to measure that change honestly before the model goes into the field. Local training on edge devices is the exception, not the rule, and the reason is mostly practical. The central question is when a device should only run a model, and when it should actually update that model itself. Most edge systems are built to make predictions where the data arrives. That keeps the device lightweight, while the learning step usually happens somewhere else. Training asks the device to do far more bookkeeping than inference. It has to store intermediate state, compute gradients, update parameters, and move more data around, so the load on memory, energy, and heat rises very quickly. A few edge cases do make local learning worth the cost. The useful patterns are narrow, but they show up repeatedly in real systems. The bar is high because the device has to earn back the extra complexity. If the task does not give a strong reason to learn locally, centralized training is usually the better choice. One good fit is anomaly detection, where healthy behavior is common and failures are rare. A device can learn the normal pattern on-site and then watch for drift away from that baseline, especially when a remote location has its own local signature that is hard to capture elsewhere. Another fit is personalization through enrollment. The user provides labeled examples on purpose, and the device turns those examples into a compact representation that can be matched later without running a full training pipeline every time. Access badges, face unlock, and voice authorization all use this idea. The system is learning a specific identity profile, not rebuilding the whole model, so the adaptation stays narrow and manageable. A third pattern is when a label can be inferred from context instead of being typed in by hand. Usage logs, charge cycles, and similar traces can act as indirect targets, which makes forecasting and scheduling possible with local learning. Even when local learning is possible, it still has to survive the realities of deployment. Resource limits are only part of the problem. Stability and control matter just as much. The real challenge is not only cost. A learning device has to remain predictable, maintainable, and safe while it is changing its own behavior in the field. That combination makes field training fragile. A device can drift, overfit, or become unstable, and those failures are much harder to debug than a centrally managed model that follows a controlled release process. Federated learning sits in the middle because devices can contribute training signals without sending raw data back. Even so, it brings orchestration overhead, communication cost, and security issues like poisoning and unreliable participants. The common production path is still to improve the model in the lab or cloud, and then push the new version to the fleet. That keeps monitoring, rollback, and auditing much simpler than letting every device rewrite itself. For deployment teams, the main decision is whether local adaptation really earns its place. Most of the time, the answer is no, but the few cases where it is yes are easy to name. When a task depends on cheap labels that only the device can obtain, local learning becomes more plausible. Personalization, anomaly detection, and privacy-sensitive workloads are the main places to look because they can justify the extra cost. The normal life cycle is still centralized training, centralized tuning, and centralized refresh. Local learning only makes sense when the device can recover labels from rarity, enrollment, or association. A simple rule helps separate the rare cases from the default ones. If the device cannot get useful labels cheaply, it should not be training. If labels are cheap and the task truly benefits from edge adaptation, local learning can be justified. Otherwise, keep training in the center and let the device do what it does best: infer quickly and reliably in the field. On-device training only makes sense when the device truly needs to adapt locally. The important question is not whether it can learn, but whether local learning is worth the cost and the risk. Most edge devices are built to infer, not to train, because training consumes the resources that edge hardware has the least of. Data movement, compute, memory, energy, and connectivity all get stressed at once. A forward pass is light work compared with training. Training has to keep intermediate values, compute gradients, adjust parameters, and do that over many passes, so even a small model can become too expensive for a battery-powered node. Local learning becomes plausible in a few narrow cases, and they all come down to one issue: where the labels come from. That label source determines whether the device can train without a lot of extra infrastructure. If the labels are easy to obtain, the case for learning on the device gets much stronger. Predictive maintenance fits this pattern well. The device watches healthy operation for a long time, learns the normal baseline, and later treats deviations as signals worth flagging. Personalization uses labels the user intentionally provides. That works well for matching and embedding-based systems, because the device only needs to learn the examples that matter to that person or installation. A device can also learn from patterns in history, even without a direct class label. When one action regularly follows another, that sequence becomes a useful training signal for prediction and ranking. Federated learning belongs in the same conversation, but it solves a different problem. It changes where training happens. It does not remove the need for labels, coordination, or trust. Spreading training across devices can reduce raw data movement and support privacy goals, yet it also creates overhead. The system still has to manage updates, bandwidth, and integrity checks, so the hard parts of training do not disappear. It is best treated as an architecture choice, not an escape from the cost of model governance. The raw data may stay local, but the training process still needs supervision and evaluation. A typical edge deployment keeps learning central and inference local. Riverwatch is a good example of that normal pattern. Train once, deploy widely, and update only when the model really needs to change. The usual life cycle is straightforward. A team trains the model offline, checks its behavior, then ships it to the device fleet, which spends most of its time making predictions from fresh sensor readings. When the model needs improvement, the safer move is to replace it remotely rather than let every device rewrite itself. That keeps testing, rollback, and audit much simpler and preserves control over model quality. Local training is justified only when the labels are easy to get, the adaptation has real value, and the consequences of error stay limited. If any one of those fails, central training with remote updates is usually the safer choice.